Okay, hello. Is this volume good? Okay, so yeah, welcome to the last week of LLF Phase 1. So congratulations for making it this far. Thanks for sticking with us the whole time. How are finals going for you guys? I see a grimace. Good. How about you guys? I'll take that as bad or stressful. But still, thank you for showing up despite the finals. Because don't worry, we have finals too, and we're also taking away our time to do this. So yeah, you might be asking in practice now, how is MLF applied? So to be direct with you, the stuff you learn is directly applicable and not useless, of course. And the whole point of this lecture is to paint the big picture here. We're going to learn about what, deep learning techniques and architectures are typically used in modern machine learning. And a side note, this would be a preview of what you'll be learning in APS 360 and CSC 413. Which one of you guys are CS or art sci here? Raise your hand if you're like art sci. Any engineering here? What eng? What engineering are you in? Nice. Right here? How are you liking it? Oh, where you where you from? I'm just wondering. Team U? Nice. Well, it's great you're here. Thank you. I didn't expect someone from a different school to be here, but that's cool. Okay, so first of all, what is deep learning and why? So this is the formal definition of deep learning. It's a pretty convoluted definition. So formally, it's defined as a machine learning method that learns multiple levels of abstractions over data end to end. You will understand what this means as we go through the slides. But yeah, I'll give you some time to copy this down. But what all you need to know for the time being is it's just neural networks with many, many layers. So it's quite informal. It's because the field is just so broad and there's so many different things you can do with neural networks. So what we're gonna take away today is we're gonna talk about three of the most common or most important or commonly used deep learning architectures. Um, and yeah, let's get into it. So, who is here for week 3 to 4? Were you guys here from week 3 and 4? Yeah, so we call neurons, right? So we looked at how we are modeling, our machine learning model after a human neuron, right? So our inputs will just be some vector. We multiply it with a matrix, which is our weights. We add some bias and some activation function. You guys remember this, or this rings a bell for everyone, right? I'm just wondering, does anyone remember one of the activation functions we used or no? It's fine if you don't. Like, we talked about the ReLU. Do you guys remember the ReLU? Yeah. So, let's look at neural networks, right? You guys remember this diagram as well? I'm sure you've seen this, right? Remember in our old neural networks, we had an input, right? And we passed these input features through some hidden layers and then get some kind of output, right? So you may be asking, why neural networks? Why deep learning? So recall some classical machine learning algorithms we looked at, right? So I remember some of your faces on the decision tree lecture, so that's good. Algorithms like decision trees require manual feature engineering. So manual feature engineering is when you need to manually transform raw data into meaningful inputs and features that your model can choose from. So what does that actually mean? This is best represented with an example. So we have done some image classification. So you may know that an image is just a big grid of numbers and pixels, right? So you have all of these raw numbers, which might not actually be useful, right? Because in an image, you can have things like an edge, right? For example, in that picture of a cat, uh, I don't know why this thing is in the corner. I don't know if I can hide it. Okay. In this image of a cat, you see those like edges around the helmet. Those are important features of the image, right? Because it shows there's like a helmet on that cat. Or there might be changes in brightness in that image. Or there might be different kinds of colors in that image. The problem is that with this matrix here, you will actually not have a representation of what those are in these numbers. Does that make sense? Do you agree that these numbers are just numbers and don't have much meaning to it? Does it make sense? Okay, so what does deep learning do? Deep learning just allows you to pass the raw pixels into the model. So models like CNNs will allow you to do automatic feature learning, which I will explain more in detail later. And more benefits of deep learning. Besides automatic feature learning, deep learning can do lots with complex data. So deep learning, you can work directly with pixels, waveforms, and text embeddings. ChatGPT is actually trained on text embeddings. And furthermore, deep learning scales very, very well. So oftentimes, if you have more layers and more data, that oftentimes leads to better performance. And in short, deep learning is great. The fact that ChatGPT is trained using deep learning should tell you that deep learning is currently the state-of-the-art technique used in machine learning. So, does anyone have any questions about deep learning in the meantime before I start getting into some common architectures? Are we good to go? Okay. So let's look at our past attempt with images. So who remembers what this is or what we looked at? Remember seeing this in the past, right? So in weeks 3 to 4, we looked at this data set and we looked at like a 28 by 28 pixel image. It was a grayscale image, right? And our goal at that time was trying to classify these handwritten numbers with a neural network. So you may remember our approach to this problem, right? We just took this image and we flattened it into a vector, right? That's all we did in weeks 3 to 4. And our goal was to do this at the end, right? We transformed this image, right, into this vector here. And what we did with that vector is we passed it into a neural network so that we can predict whether or not is 1, 2, 3, 4, 5, right? You guys remember this, right? So, for example, let's say I want to make a model that classifies whether or not something is a number 5 or 7 or neither. This is how we would usually do it, right? So, what may be some issues you foresee with this approach? I'll give you guys 30 seconds. So, what may be some issues with this approach here? So, first of all, this image, right? This is a grayscale image, so it's only black and white, right? But the pictures you take on your phone, they usually have colors, right? So the first problem that it is when you use like RGB images or when you have more complex data, there's going to be way too many parameters. So just for this 28 by 28 grayscale image, right? We already have 764 inputs, right? Because that's 28 by 28 pixels of zeros and ones, correct? So if our hidden layer has 20 neurons, if you connect all of them together, that is already 50,000 features. That is so many features already that you need to learn. But nowadays, we work with RGB images, right? They've been around for so long. So if we just work with grayscale images, that's ancient. We're not going to go anywhere with it, right? So let's say you have now a 256 by 256 RGB image. Well, what's going to happen? The image itself has like 200K inputs, right? And with 200K inputs, if you have 20 neurons, that's 4 million features, 4 million ways you have to learn. That is going to explode for larger images, right? That is way too many parameters, way too many numbers you have to update. That's very expensive. That's not practical at all, right? We only have a limited amount of resources when we do deep learning. So that is the first problem. So is it clear for everyone the problem with our original approach? The second approach, the second problem, you're ignoring the geometry of the image. So if you look back here, you're, like the word says, we are flattening the image. So when you flatten the image, you're going to lose geometrical understanding of that image, right? When you flatten it into a vector, you will actually not know what pixels are next to each other, essentially, right? Like, let's say I'm a pixel, right? You have 8 adjacent pixels, right? One here, one here, one here. That spatial information is lost when you flatten the image, right? And when you flatten it, that means it's going to be harder for you to detect things like an edge or shape or where things are relative to each other, right? Because they're flattened. Does that make sense? Yep. So, for example, we didn't tell you in the MNIST data set, all the numbers are centered. So, if you pass in a screwed up image, if it's rotated or off center, the model is actually gonna suck. So if you pass in an input like this, it's gonna actually perform terribly because your model is so used to all of the numbers being in the middle. It actually doesn't know spatial information, right? And logically speaking, let's say you are the machine learning model, right? If you want to detect a five, ideally you want to detect a curvy pattern on the bottom and a sharp turn at the top, right? So that it's a five. That spatial information is essentially gone when you flatten that image. Does that make sense? So, what is our solution? Our solution is convolution operator and the kernel. These are some big boy words, but don't worry, I think they're pretty intuitive once you see a visual example. So, the convolution operator, what is it? It is the heart and soul of convolutional neural networks and any kind of deep learning model involving images. So, mathematically, you don't actually have to know what it means, but I'm just going to say anyways. Convolution is it describes how the shape of a function is modified by another. You don't need to know this. If you take a signal processing course, you'll learn about this very well. So if you're in ECE, you will learn about this in a lot of detail in your second and third year. But yeah, I was in ECE, that was my worst course ever. But anyway, in our context, this is what convolution is. So this is where you actually need to pay attention. Let's say I have that image, right? I have a 5 by 5 image, and I have something called a kernel. So a kernel is essentially a smaller matrix. What you're going to do with this matrix when you do convolution is this. There's a long description there, but you can just follow what I'm doing. You see this small k matrix here, right? You multiply it element by element, so like 7 times 1, and you add it to 2 times 0, and you add it to 3 times 1, -1. You can see where this is going, right? And then you add it to 4 times 1, add it to 5 times 0, blah, 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 and you put the sum in a new matrix. Is that clear for everyone? So another one here. I have the numbers here this time. So what's going to happen is, right, you do this for the left corner, and you're going to slide this kernel across the matrix. Does that make sense? So in the second iteration, we slide this kernel over here. So that you get a new result and bring it. Is that good? Does that make sense? Yep. So that is what convolution is, right? You don't need to know that stupid mathematical formula. Um, but yeah, if you really want to write it down, you can write down like the procedure, but I think that was like a clear enough demonstration of it. So you may be asking, well, there's also a mathematical formula. You don't need to know it, so it's fine. So you might be asking, well, what are we doing this for? Why are we doing convolution? Well, first of all, what does it actually do, rather? So you know how Instagram, you can add filters to your image, right? This is what exactly kernels do. A kernel is also called a filter. So, for example, if you have a matrix of that, so like all ones and like divided by 9, if you put that through your image, this is a blur filter. So this, if you can kind of tell that this matrix averages your pixels, right? If you think about it, because look, you're adding every pixel in that grid and you're dividing by 9. So that's like an averaging filter. Does that make sense? So, what you need to know is that a kernel will transform your image into basically a different kind of representation of the image. That makes sense. Another example is an edge detector, right? You can pass your image into a kernel, and the output can be like this, that highlights the vertical edges and the horizontal edges, right? So you might be asking, why do we need to do this to images? Well, I brought up earlier that when you flatten an image, or when we worked with image in the past, we've been ignoring these kinds of geometrical understandings, right? We've been ignoring these edges, we've been ignoring these colors, but with filters, you can actually highlight these features, right? Like on Instagram, there are definitely filters that might highlight your eyes or might highlight your lips or things like that. When you do image classification with machine learning, there are things you want to consider important as well, right? If you want to think about, if you want to classify a cat or a dog, you want to, highlight the whiskers or highlight maybe the ears of a cat. That is what kernels allow you to do. So, any questions? I know there's a lot for now, and I hope it makes intuitive sense. Are we good? Okay. Yep. So like I said before, this is like applying Instagram filters, right? With a filter like an edge detector, you will have a representation of an image where the edges are highlighted. That's just a repetition of what I said before. And since we have no questions, we'll move on to our next one. Because this should be very crystal clear to you before we move on to CNNs. So one last time, any questions about what a kernel does, maybe what it outputs, maybe some mechanisms? If no questions, I will move on. We good? Okay. So convolutional neural networks. In our old pipeline, can we all agree this is what we've been doing in the past? So we have this image, and like I said before, we flatten the image into this vector, right? And then we pass into a neural network and then output some classification. That's what we were doing, right? With the MNIST data set, right? We have these images, you pass it to this neural network, and you output whether it's 0, 1, 2, 3, 4, 5, blah, 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 right? Now, for convolutional neural networks, it is just the exact same thing, but in between the input and the flattening part, you're going to have this new part here. This new part is called feature learning or feature extraction. So all feature learning does is it uses kernels to learn a more meaningful representation of the image, right? So for example, let's say I have a cat, right? A more meaningful representation is if I output a version of the image that highlights the edges, right? We want to see where the cat ears are. We want to see where the cat whiskers are, right? So how does that actually work? So when we perform classification, you still need to find the image. But the good thing is, at this part, instead of the raw image, you're going to have essentially multiple versions of the image that highlights different features. That is more meaningful than the raw image, right? If you have a cat, I'll show you an example afterwards. So here, right? Let's say you have this cat here, right? This cat, you pass it through your kernels, you're going to have different versions of this cat that highlights different features, right? So these different features are better, like they're more meaningful, basically, right? You can see like in this image, it highlights more of like the black and white parts. Um, so yeah, when you do convolutional networks, this is what happens. So first, you will initialize the kernels randomly, right? So you know those matrices that we just had, like the 3 by 3 matrices. You're first gonna initialize to random numbers, right? You initialize to, and then next, what's gonna happen is when you train your model, you put your image through that kernel, right? So that multiplication we did, and it's going to output some meaningful representation here. And then you're gonna flatten the network and output whether or not it's a cat. Now, do you guys remember before, right? You know how we made a classifier network, right? And we used the output to see whether it was right or wrong, right? And you guys also remember loss functions, right? We use the loss function to train the weights of the network, right? For convolutional networks, you're also going to update the weights of your matrices. This is very, very important. So what's going to happen is, I'm going to repeat again, right? You have this cat image. When you train it, you put it through these kernels. And you put it through these kernels, you have multiple versions of this image, right? And then you flatten these images into one vector again, and you just do the same thing. Except when you go back and update your weights, in addition to just updating your classifier weights, you will also update the weights of these kernels. Any questions? This may be a very new concept. Or anything you're not clear about, feel free to ask me. Yeah, yeah. So the kernels are random at first. So you know how I talked about there's like a blur filter, there's like an edge detector filter. Those are you can think of as pre-made filters, right? When you train a model, you want those filters, but you want to learn those filters. So essentially, let's say I have like 4 filters here, right? Like I'll initialize it randomly, So since it's random, the images that's gonna output is gonna be very bad, right? Because the whole point of this is to highlight like different features of the image. At first, you're gonna be highlighting some random features, and of course, the representation you get is gonna be very bad. But if it's very bad, then your loss function will be very high, and then it's going to update the kernel so that the features become more meaningful, if it makes sense. Like for example, like a cat, right? At the beginning, these kernels are random. So when you pass it through, you can all agree this vector is going to be garbage, right? Since it's random kernels. If it's garbage, well, if you pass into your classifier network, the output's also going to be garbage. So it's going to say, hey, this thing is a dog. But since I output something wrong, the loss function is going to be very high. So do you remember how in the classifier, right? If your output was very bad, you're updating your weights so that your classifier network outputs something better, right? Like your neural network outputs something better if you update the weights. You're doing the same thing for the kernel. So when you update the weights, you're making a better kernel so that it's making more meaningful representations of the image. So that it makes your classification easier or more accurate. Does that answer like your question? Yeah. Okay, so now after your kernel, what is actually the output? So I'm simplifying things. I've been saying, hey, I pass this cat into these kernels and I see these smaller and wacky images. But what actually are is the output of the kernel, right? So any ideas? What like when you do let's say I have an actual image, right? And I pass through that kernel, what actually is gonna be this output? Like, is it gonna be bigger? Is it gonna be smaller? What is actually gonna be outputted after this? Well, we'll see. So, first of all, you can agree that if your image is initially really big like this, right? You're essentially making a smaller image by doing this, right? Now, think about what we talked about earlier, right? Earlier, we said that there is way too many features when you flatten that vector, right? So, if we have a big image and we can make the image smaller while maintaining the meaningful features, doesn't that mean that we will have less of these features when we flatten it so that we don't come across the same problem? I'm going to repeat, right? If you can make the image smaller, right? Doesn't that solve the problem of this, of too many parameters? If you can make the image smaller while maintaining all the important information, we're going to be solving this problem, right? So essentially, the output, like I said before, is just a smaller image, but with different features that's being highlighted. Does that make sense for everyone? Okay. So we'll get into some math here. So we've been looking at 3 by 3 kernels, right? Hello? 3 by 3 kernels. So you can actually customize your kernel a lot. We're not just limited to 3 by 3 kernels. So you can edit the size of your kernel. It doesn't have to be a square, although there is a paper that demonstrates that you can effectively use a 3 by 3 kernel on anything, but I'm not going to go into that. There are also things called stride and padding, which I'll get into about kernels. So it's fine if these terms sound foreign to you because I'm going to talk about what they are as well. So you know the 3 by 3 kernel we had, right? And you know that 5 by 5 image we have down there, right? And you know how when we slide that kernel, we're only sliding it to the adjacent, like to the next like pixel. You don't necessarily have to slide to the next pixel, right? You can see here, it kind of just jumps 2 pixels, right? Can everyone see that? You know how before this grid, if you are to slide your kernel, it's gonna be here instead of here, right? That is what the stride is doing, right? Now, what the stride does is this means your output is actually going to be smaller. So that determines your output resolution. Any questions? So I guess a refresher for you. So today we're talking about deep learning. So deep learning is basically like the modern um, approach to machine learning. Currently, we're looking at convolutional networks, and you remember these diagrams, right? Remember how before we were taking this image, flattening it into a vector, and then putting it through neural layers, right? We talked about how there are problems with this approach. So to summarize, the main problems with the approach is that there can be way too many parameters, right? So if you have like a 256 to 256 image times three, that's this many inputs. If you have 20 neurons, that's this many features. That's bad, right? And also when you squish an image to a vector, geometry is gone, right? So that's what we're trying to tackle with um, kernels. And I guess to summarize, what kernels do is they basically you can kind of see. I hope you can see mathematically what happens here. So you like multiply each element, and you get this element here. Yeah, so it's a good refresher for everyone as well, in case you're forgetting. Kernels, they basically make your image smaller, and they highlight certain features of the image. That's all it does. Okay, back to the original slide. So now I'm presenting. You know what's wrong? So, any questions about the kernel stride? Does everyone understand? Yeah. What the kernel? Yeah, it doesn't have to be 3x3. Yeah, kernel can be anything. But there's a paper out there that says you can use 3x3 for anything. I forgot the name of the network. It's the yeah, or VDP network. Yeah. Yeah, yeah. So this kernel here, it can be any number in there. Yeah, yeah. So it's not restricted to this. So what's gonna happen is you see your seven up here, right? Your seven multiplies by that one, and then your two multiplies by that zero, and three multiplies by that negative one. You add it all and put it in there. Yeah, yeah. The values of the kernel can be of the matrix. Yeah, this matrix. Yep. So you remember before with neural networks, you have your loss function, you update your weights, you update the kernel as well. Okay, and how do you multiply the 3 by 2 matrix? Hmm? Yep. Yep. So 3 by 2 matrix, you see how this is shaded like dark and blue? Then only these two rows will be shaded dark and blue. So if you have a 3 by 2, right, matrix, then instead of multiplying like 3 by 3 values here, you'll be multiplying the 3 by 2 values here. You'll still be outputting it into it. The size will be different. Yeah. If it's 2 by 2, then let's say it's 1010, right? You'll just do 7 times 1 plus 2 times 0 plus 4 times 1 plus 5 times 0. And that's it. You add them and you put it into your. No, that just depends on the size of the kernel. Don't worry. I'll get into output size. So don't worry. So yeah, and to update you as well, your kernel, you know how we slide through the kernel? Well, I didn't explain that to you, but when you slide through the kernel, you don't have to slide by 1 pixel necessarily, right? You can slide by 2 pixels. And also next thing is zero padding. So if you're with your input image, you should actually add zeros around your image border. Because think about it this way. If your kernel is just multiplying by this corner over there, right? Your left top pixel will be only considered once. Does that make sense? If we go back to this diagram, right? You're only going to look at your left top pixel once. But you might have really important information in the left top corner. So you will just tackle this by using zero padding so that you consider these edges more often. Oh, back to your question then about output size. So what is actually going to be output size? Well, there is a formula for it. Do you guys know the floor operator? Floor rounds down to the lower integer. Rounds down. Floor, yeah. So that's floor, yeah, that's what so this is just a formula you need to follow. So for an input size, you will add 2 times the padding, subtract the kernel size, divide by stride, floor it, and plus 1. That's your output size, right? So if you have like a 28 by 28 image and you have a kernel of some size, your output image is most likely going to be smaller. Now, this should tell you right away that the stride will reduce your resolution, right? This is in the denominator. So if you have a stride of like 2, this number is going to be much smaller. Oh yeah, stride, let's go back here. So in our kernel, usually you see this kernel here, right? 3 by 3. Usually you slide it through like this. Okay. But you don't need to slide it through to the next place. Or you can slide it through to like to the top. Okay. So what that does is that makes it a little small. Okay. divided by 2, you count the third column 2 times. 2 times. Yeah, that's fine. Yeah, that's fine. It's fine, yeah. Like you just do this, right? And then you just look. And you only because you said let's be at padding because we want to take more into account the. No, that's why you have padding. So this example I don't have. Oh, okay, okay. Yeah. I'm just trying to show the operation of this example. Yeah. But good questions. That points out why we need those kinds of like operations. So any questions about stride and padding or output size? So you might be asking, well, what about RGB images, right? Because if we look at the example we did in the past, you will realize this is just a matrix of one layer. But how many layers does an RGB image have? 3 layers, right? You have an R, you have a G, and you have a B value. So what's gonna happen is so I just have a cat there, but your RGB image is actually gonna look like this. Does that make sense? You will have your width and height as well as your depth. So your depth will be 3 because it's RGB. So if we were doing a 3x3 kernel with a grayscale image, you will need to do a 3x3x3 kernel if you're using an RGB image. This seems weird, but I will go through a visual example to improve your understanding. So let's say you have an RGB image. Your RGB image is 3 matrices, right? One for red, one for green, one for blue. Because it's RGB, each filter you have needs 3 layers. Does that make sense? Each layer needs to correspond to of the filter needs to correspond to each layer of that image. But the rest of it is the exact same, right? You see here, you're still doing the same kernel operation, right? You're still multiplying the weights of this filter and adding it to the output. Yep. Yep. So when you have an image, you can use multiple kernels. Yes. With the cat image, right? I said before, you want to emphasize the colors of the cat, the edges of the cat, the differences in brightness, right? Well, if you want to consider all 3 of those features, then use 3 filters. And the key here is for each filter you have, that would be the amount of layers in your output. I'm going to repeat this again. You have 2. Okay, first of all, everyone understands why you need a 3x3x3 filter, right? For an RGB image. So if I can use multiple filters. So not necessarily yeah, that one, like I said before, doesn't have to be 3x3. So that one you can change whatever. But if it's an RGB image, your depth has to be 3. 3 by no, the depth is 3. Depth is 3. Other variables can be yeah, it can be yeah. So like this guy right here, like it can be 3 layers. It needs to be 3 layers, but it can be like much bigger or much smaller. Right. So what's happening in this example is you see this matrix, right? You use this filter, you get this number. I'm not gonna do the math because I'm not gonna right? But here's the thing, right? If you have 2 filters, what's gonna happen is that each filter will have its own output, right? So let's just ignore the G and B first, right? Let's say you're looking at this image here. For my first filter, I'm gonna have 1 output matrix. For your second filter, you will have a second output. Okay, so for this first filter, you do all this math here, slide it through the image, and then you will have this first output here. And then you move on to your next kernel. You do the same thing, but except do not add it to this, you add it to a new matrix. Does that make sense? So let's go back to the cat example, right? Yeah. I'll use the kernel or like ways that we are going to change. Yep, throughout the training process. Yeah. So, for example, let's go to cat. I love the cat example. We cannot initialize it by putting only 0. You initialize it with random values. Random values. Yes, and it's trainable. So when you do a loss function, you're updating the kernel as well. Yep. So back to the cat example, right? If this is an image of a cat, that might be your filter for highlighting the edges of the cat. So what's going to happen is your output here is going to be an output image with the edges highlighted. This might be the kernel for the different brightnesses. So this output would be an image of the cat that has its different brightnesses highlighted. Does this make sense? That's why I have this diagram over here. So if you have four kernels, you're gonna have four different filtered outputs, right? And also, it doesn't have to be color. You can flip the cat as well, whatever the kernel does. But any questions about the kernel operator? It's quite a lot to take in.
Can you do this quickly?
Yeah.
Not
Yep, no problem. So this example also has a bias term, so I'm really annoyed with it. That's why the math doesn't work out at first. So what's gonna happen here is with your if you look at yeah, this kernel yeah,
If zero times the first column is zero, the second zero times the second column.
Yep.
Then you have one plus the bias.
Yep.
Equals two.
Yep.
You look at
Mhm.
the-
Yeah.
So what is it just for R?
Which one? This one?
Yeah. Just for R for zero.
I kind of forgot. Hold on. Give me a second. Um, okay, so you'll do these filters and then oh, my bad. Okay, so back to the RGB, right? I kind of ignored about RGB. So you have three matrices here, right? You go through this filter by you you understand that we put this filter on the R, we put this filter on the G, and you put this filter on the B, right? You do this multiplication, right? And then you'll add that result to here. So you know how this times this will correspond to your left corner, right? So you do this times this plus this times this plus this times this plus the bias, like as U2.
Let's look at the one that is here.
It's this one.
Okay.
Yeah, so my mental math is pretty slow. Let's just do the math together then. So this one you don't multiply anything except the one, right? So one times -1, -1. Here you don't multiply anything except these twos here because there's two zeros here. So um one times -1, -1 plus two times one, that's one plus yeah. So when you multiply this, right? You multiply numbers correspondingly. So zero times no correspondingly, and you add it. It's like dot product. Sorry, I should have told you that. I should have told you that fine. Sorry. Yeah, yeah. So here you only have to care about the one here, right? Because all these are zeros. So one times yeah, so that's -1. And then you add two times -1, that's -3. Yeah, -1. If you do the math here, add the bias, that's two. Yeah, yeah. No, good question. Good question. I should have clarified that. So any questions about how this is done? Or any questions about the diagram? It's a pretty confusing diagram when I first came across it. Is everyone find this diagram? Okay, so there are two filters applied to the image, like I said. This produces two layers in the output. So what this means is your CNN is going to learn two 3x3 kernels. So when you do backpropagation, this example we have two filters. Your choice. Your choice. It is a hyperparameter. Yep. Now more filters don't necessarily mean better. It is up to you to tune it and see how it goes. So let's do an example here. Let's say you have a 28 by 28 by 3 RGB image, and we have four kernels with these properties. What's the output dimension? I'll give you guys a little bit of time. I unfortunately don't have the formula on here. I should put it on the slide. But those of you on computers, you can. I don't know if Jessica posted the slides, but um, this is the oh, it's not so long ago. It's here. That's the formula, and these are your conditions. You know what? Right now, I'm literally just gonna paste the formula onto the slide, so it's better. Oops, there. Give it guys like a minute or so. I clicked by accident. Yeah, yeah. Okay, any answers? Yep. The format of your dimension should be like 28 by 28 by 3. Like the format should be like this tuple here. There's one more part of the answer. By 4. The number of kernels determines how many layers you have in your output. No. What's going to happen is with your 28 by 28, you're going to shove it into this formula here. This formula should get you a 14, right? So you get a 14 by 14, and you have 4 kernels. So you will have 4 layers of outputs of 14 by 14. Does that answer or procedure make sense for everyone? Are we good here? Okay, we're good here. So that is literally all you have to learn for CNNs, because what's going to happen is that you will have your input layer and you will just do all of the convolutional layers to get a better, like I said before, a more meaningful representation of the image. That is all you need. Everything after that just follows what we've been doing with our linear neural networks. So I do not have enough time to go into that. But I can summarize to you what pooling is. Pooling, it consolidates your information. So if I can go through a very quick example. So you have this it's better if I just pull up a diagram. But you can think of pooling basically is you can think of it as a kernel layer, but you don't train the weights of it. Well, it's not really a kernel layer, but let's say I want to do something called 2 by 2 max pooling. So 2 by 2 max pooling, what it does is it grabs the maximum value for every 2 by 2 block, and it just puts it in the output. It's just an example of pooling. So pooling, if you search it up, you very easily find an intuitive understanding of what it is. Pooling, it just consolidates information. So you make it even smaller, right? So for example, max pooling, right? Max pooling, if it's 2 by 2, you grab the biggest number in this 2 by 2 image. So, okay, what happens is when you have this image, you put the kernel, you get like a smaller image, right? Usually you'll put another kernel through it as multiple layers. Yeah, yeah. So let's say you have this matrix and I want to do max pooling, right? Max pooling, 2 by 2 max pooling will be like this 2 by 2 matrix, just grab the maximum value and put it to make it an even smaller image. Now, why would you do max pooling? Maximum may extract you the most important information while making the thing smaller. Because one of the problems we talked about in the past is that this guy here is way too big. There is way too much here. So what pooling does is it squishes your information even more like condensed. I just don't have enough time to go through that. Sorry. So usually what will happen when you do a CNN is that you have your input image here. You'll put it through a set of kernels. A set of kernels is called a convolutional layer, right? So you put it through a set of kernels, you may do some pooling, and you put it through another set of kernels. Do it until you're happy with the representation of the image you have here. And once you put it through enough kernels and stuff, we'll just flatten the vector again and just put it through your fully connected neural network. Any questions? Any questions about CNNs? Backpropagation? Well, how do you do what? Yeah. So it's literally the same thing. So like the kernel weights is trained the same way your weights of like your neural network would be trained. So yeah, I have a diagram for this, don't worry. So you know how the loss function will backpropagate into that classifier network? Yeah. That loss function also backpropagates into your kernels. Okay, propagates. Yeah. Even before the input. Okay. For the neural network. Okay. Because when you flatten, you have the input for the neural network. Yep. So Okay, don't worry. I'll go through a procedure, right? I have the cat here. Let's say I'm training my network. I have my cat. I put it through kernels. I get a bunch of paths. And switch these paths into the vector. You put it through a classifier. It's that cat. Depending on whether or not your answer is right or wrong, that loss function is going to propagate into both this and that. Does that make sense? Yeah, and that's basically it for CNNs. That is usually what is done with images. So I'm gonna, any more last questions? If not, I'll hand it over to Aaron to talk about RNNs and recurrent network.
So now let's talk about sequence models. So first let's talk about what kind of data that the sequence models deal with. So there's some data called time series data, which is a bit different from like most of the data you've seen so far. So lots of data you've seen so far is like um, does not carry temporal information, right? For example, you're doing like a house price prediction, then you probably have features like the like size of the house, like number of rooms, right, or the location. But those things doesn't really carry any temporal stuff within it. But some data, like or actually lots of data in the real world, carry some sort of temporal information, or you can think of it like the order of the data matters, right? For example, like stock data or your weather forecast, right? And then books and my musics are my favorite examples because for books, the order of the words matters. You read it, right? And then also same for music. The order of the notes matters. Otherwise, if you just randomly shuffle the words for the notes in music, you couldn't really like understand what they're saying or what the music is. It would like completely change things or the meaning, even if it might make sense though. Or sometimes it just doesn't make sense at all, right? Um, so what's the problem of like traditional neural network, which you guys learned about deal with time series data? I'll just give like a here. Let's say you have this network. Uh, why cannot like this network cannot process information like temporal information efficiently?
Can you ask maybe
Hmm? Time feature.
the teacher has 21 we can do that.
Uh, you could like how do you do it? Because in this case, each let's say just do books, right? So or instead of like book, let's just say you have a sentence, right? So you need to basically tell the model which words comes first, which words comes second, right? Like how do you do that? If you're like from what you're saying, right? Because it's not unique. Like there's not like it's not one time step. It's like every single time step, right? So yeah, that's basically one of the issues because let's say here you have two inputs, x1 and x2. You can think of them as like two words or whatever. But if you give it just to the neural network, it doesn't really know which words comes first, which words come second, right? Because it sees the input like at the same time, basically. And also, there's a big issue that it's not really like noticeable here, but is that let's say I train a network because for all the neural network, your number of input is fixed, right? So let's say I try to train a network that takes in 5 words as input and whatever I do, like classification, whatever task it might be. But if I have a sentence of 6 words, there's no way you fit that into your neural network, right? Because you can't fit more features than like your neural network dimension would take in unless you do some feature augmentation or whatever to condense the number of features you have to match exactly to be the size of the input, right? So yeah, those are basically the two issues. First, first, there's no temporal like neural network doesn't learns about temporal information, and second, it doesn't allows more feature than it would. So now let's introduce something called recurrent neural network. So um, we're not diving into details, but I'll give like a high level overview.
So this weekend, what is the future about all the vocabulary and then the one?
You mean for the words input?
Yeah.
Like you have like a dictionary. Is that what you mean?
Yeah.
And then
Vocabulary.
yeah.
And then with zero, the word is not in the sentence, and one,
Yeah.
the word is in the sentence.
Yeah. 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 What's your question then?
Yeah, so this word is what I said.
Uh, like it does. That's what we did in week 6, right? But it's like it doesn't carry too much intrinsic information. Like it doesn't carry too much like details about the word. Like yeah, it basically tells you which word is in the sentence, but it doesn't tells you in what order, right? Or like even it doesn't tells you how many like because the same words might repeat in the sentence, and it even doesn't tell you that. So it's like it tells you something, but not too much. That's basically yeah what it says. Um, yeah. For recurrent neural network, um, it's a model that deals with sequence data, of course, and it gives so it looks at the input instead of here, like we look at it in all the inputs at once, right? Recurrent neural network looks at the input sequentially and also gives output sequentially. So as an example, it's like how you read a book, right? You read book, you don't read the entire like book all at once, right? You read like word by word. So it's like a sequential process. And the network does the same thing. So here, as you can see, both for the image, both on the left and the right are the same representation of the same network, but on the left is like the left. No, on the right, it's a unfolded version of the network, but they're like kind of the same thing because you see the on the left, the V just goes back to the network, so it's kind of like a recurrent process. But what's going on here is like H is your model. You can think of it sort of as a just normal neural network that will takes input and gives you some sort of output. And here V is the hidden state. And I'll just go through like what every symbol means, and then we can like put it all together. Okay. So L is your output, and then X is your input. So like the capital X on the left is your entire input. You can think of it as like a sequence of words or like lots of words. But how the neural network process this is it actually processes word by word instead of all the words at once. So what's going on here is like we can see, as you can see on the right. So let's say I'm processing like a sentence of 3 words or 4 words. Like let's say I love machine learning, right? So before, what your neural network does is that you input all 4 words into the neural network at once, and you get some sort of output, right? But for recurrent neural network, it will look at words one by one. So let's say at the first time step, the neural network will just look at the word I, which is the first word, right? And then it will give some sort of output, whatever it could be, or you could choose to ignore the output. Like you could choose to make the output or not because it depends on the tasks, right? But what's going on here is like you will have this v vector going out after looking at the first word, and we call this v the hidden state. So it's kind of like your activation between layers. Not too exact, but you can think of it as something like that. And this vector carries information about like what the network or what kind of words is seen before. Does that make sense? That's for like one time step. So you look at an input and then you try to record some information and then give it to the next step through this vector V. So you can think of this V as the context or yeah, you can call it context or hidden state. It doesn't really matter. This does make sense. Okay. Yeah, so that's for the first time step. And then your neural network process the words I, right? Yeah.
Sentence.
Like you can do like let's say genre classification for book, right? What kind of book is it? So it depends on the task, right? Or you can do like translation. So you input the like let's say here for yeah, for your input, let's say your X is English, right? And then L, you can output like a different language. I don't know, like French or Spanish, whatever. So basically, you can deal with any sort of task. So that's why I say whether you make output depends on the task. Because for translation, you can do like translates word by word, so you'll have like an output at each time step, right? But if you're doing like genre classification, you don't really need an output at every single step. You just need like you can ignore all the like LT minus zero, LT, whatever. You'll just need one. You only need to make one output in the very end, right? Uh, yeah, so whether you have the output or not depends on your tasks, but you can like always have it there. I'll see it, it shows that. Yeah. So that's for the first time step. It will look at the first words and then give sort of hidden state, which is denoted by the vector v, and then whether you have the output or not depends on the task. Right. So yeah, and then for the second time step, your model will look at the second words, which is love, right? So and then your model here takes in two sort of input. One is the current like word, right, which is denoted by x of t here at if you think of it here as the second step, second time step. And it will also take in the previous vector v because it will takes in the context, which is tells the model what's going on before, right? So like it's the past information you've seen. Does that make sense?
Like what's the size of the input? What is the size of input?
No, you treat them as two separate inputs. Like you will do some like you can have the same dimension for x and v, where you could add that. It doesn't matter. Like all you do is you can do some sort of matrix multiplication to make them fit into the same dimension, like in the end. But like the idea is that you're taking into two different kinds of input. One is the current words you have, and then the other is all the like information you summarized or like the model summarizes or seen before. So you're trying to like not only understand what's going on at the current time step, you're also trying to incorporate what you've seen before. So yeah. So
I think it's like a layer of neuron.
no, the hidden state is just like a vector. Like you can just think of it as like some sort of information denoted or condensed into a vector. Or it can be like matrix, I don't know, but it doesn't really matter. It's just like numbers, right? Like that carries information. Yeah. And so basically you do this thing over and over again, right? Like um yeah, so here because you're looking at the words one at a time, so it doesn't really matter how long like of a sequence you have. You can have like a sequence of like 5 words, then it will just take 5 time steps to process, right? And then like sequence or like sentence of 50 words, then it will just take like 50 time steps to process, but there's not really a limit on how long input you could have because it's kind of like dynamics, right? Like it can like adjust dynamically. So some characteristics of this sort of network of RNN is that it reads data sequentially by one. So it's just like how you read your book or listen to music, right? You read one words at a time or you listen to one note at a time. Um, yeah. And it uses the same network, which is called it also does something called parameter sharing. So what that means is that here you see your H network is basically the same neural network. Okay. So at each time step, you're using the same network to make decisions about what information to propagate forward or what output to give. So that means when you're doing your back propagation, you're also updating the parameter of the same network at all the possible time steps. And that means you have one network and then it learns through time. That makes sense. So basically you have like one model, but it learns a lot. Like it learns through every single time step. So you're basically updating the same set of parameters. So it's kind of like you're sharing the knowledge through time, right? So at different time step, it would probably like so let's say at the first time step, it look at the word I and then whatever the loss function denotes, your model will learn something. But that means this information will also get shared through all the other time steps. So that's all it does. Uh, yeah, and so also information are propagated through time. So because your model is sequential, so yeah, does that make sense for RNN? It's just like a high level introduction. So back propagation. Yeah, so this is a bit different. You're doing something called back propagation through time. It's not exactly like back propagation because here you carry temporal information. So you're like kind of like making an update or back prop at each time step, but we're not diving like into details about that. There's like a like entire paper about it. If you're interested, you can read it, but I didn't. So yeah, it's kind of like complex, but the idea is the same. Like you're updating. Right? Okay, so there are some problems with this sort of model though. So first thing is that your model can process sequential information, but what if your sequence gets too long, right? Because here, so your model only, this is annoying. Anyways, so uh, let's say you have a sequence of like 5 words. Then let's say at time step 5, your hidden state or your context vector B might still carry some information from the first time step, right? But what if, let's say we have a sequence of like 1,000 words, right? Then at the very like end of the process, let's say at time step like 900 or I don't know 1,000, then your model probably wouldn't remember anything about like what's going on in the first 2 words or something, right? Because here uh, your vector v is fixed. That means you have only a fixed amount of information you can carry, and they have like very long context. It can only carries a like fixed size or like fixed dimension or fixed amount of information in this case. So it wouldn't remember everything. So you have like a very long sequence, your model probably won't perform too well. Yeah. And there's also exploding and vanishing gradient problem. So because you're also doing back propagation uh, through time and through chain rule, if you have like lots of large derivatives multiplied together, it will get like exponentially larger, right? And in the same sense, you if you have like very small gradient, you're processing it through chain rule. So basically, you're multiplying lots of small numbers together. You'll get like uh, pretty much close to zero gradient. So your model learns nothing. Yeah. So these are the problems with this. And so some other smart guys invented a more advanced version or yeah, variants, you can call it, of RNN called LSTM. So LSTM sort of follows the idea of as human, we kind of have short-term and long-term memory, right? So short-term memory is uh, like what happens like a minute ago, I probably have very clear like memory of like what happens exactly, right? And I have like memory about lots of the details. But for long-term memory, like it's like I don't have too much details about like I don't remember too much details about something happens a year ago, but I might remember it's like the kind of the like storyline or whatever is going on, right? So there are like two type of memory you have. So they try to simulate that through the in the neural network as well. So RNN is basically like only short-term memory, right? Because it only looks at the hidden vector from before, right? So in this model, all it does is it introduces a new input and output through the network called denoted by the letter C here. And you can think of it as this is the long-term memory of the model. So yeah, so like for the diagram, like here you still have your H and X, and they're kind of similar to what we have in RNN because here's your input, and then H, you can think of it as your short-term memory or just your hidden state, right? Oh my gosh. Yeah. So And so all they added on a high level is just this term called the context term, which is the long-term memory of the model. Um, so the key characteristics of this model is that you have, compared to RNN, you have one more input and then one more output compared to what the heck? Okay. And it uses, so within the model, it uses some sort of information called gate, and those gates kind of decide uh, what information to remember, what information to forget about. So it's kind of like control flow, because here for the long-term memory, you're also having a like even it's like long-term, it only has a fixed amount of dimension, right? So even it carries through like it carries information for long durations through time. It will it will only like remember a certain amount of information to like there's like upper bound of how much you can remember. So those gates are used to decide like at what time what information should be forgotten and then what information should be remembered throughout like the process. Yeah. And you have like one long-term memory and then one short-term memory. So yeah. Does that make sense? Like this is a high level, so but that's like the idea. You're trying to add something that propagates through long term in addition to RNN. That's the key idea of this model. Make sense? Mm. Yeah. So, some problems with this model or sequence model in general is that first, there's no parallelization. What that means is that for before, right, when you look at like linear regression, whatever, we're trying to do like something like very large matrix multiplication, or you're trying to do batch predictions, because all those things enables parallelization, and then basically you can make computation on GPU like in parallel, so it's very fast. Right? But the issue with sequence model is that like due to its nature, it couldn't really do too much about parallelization. It's because that um, your model, like your next models, like your next time step alpha or whatever process depends on the previous time step, right? So like let's say I have like a sequence of 1,000 words, then you kind of form a chain because you cannot process time step 2 without getting the results from time step 1, right? And it's kind of like recursive. So at time step 3, you have to wait for all the previous 2 time steps. So there's nothing too much you can do about it because it's like a chain and then you can't really break any middle part. You just have to wait from the start to finish. Right. So there's not much parallelization you can utilize because you just can and the information has to go through time. Does this make sense? And yeah, another issue is about the context because even though you're carrying the context, right? But both models here only carries the like context from one direction. So it basically looks at what's only coming before, right? But sometimes, especially in I'll say in like language, what the sentence like what the previous part means can be impacted by the like later half of the sentence, whatever, right? So as an example, here you have let's say I have two sentences, right? So the first one is he went to the bank to catch fish, and in this case, bank refers to the river bank. And the second sentence is he went to the bank to withdraw money. So in this case, bank, refers to the bank with money. But for, let's say for either RNN or LSTM, it reads this, like it will read sequentially. So it reads the words he went to the bank first, right? But at that time step, both sentences will be treated as the same, right? Because it doesn't really like read whatever the words coming next. But like intrinsically, those sentences just means two kind of different things, right? But your RNN or LSTM would treat them like equally as the same thing until this, at least until this point. Right? So that's one of the issue. Like it's only the one directional context. Um, there are some like models that deal with this called like bidirectional LSTM or whatever, but we're not like looking into it. And then even that, it doesn't really like resolve the issue of parallelization. So that means it like no matter what it is, your sequence model will take very long to train compared to other models. And then it couldn't really scale up because if I like larger model, it means like your amount of training time would uh, grow like I don't know by what factor, but like it will grow without like there's nothing really you can do about to make optimization about it. Yeah. So now let's talk about transformers on a very high level because if we're gonna talk about that in details, it would probably take like 3 weeks, but we don't have time. So I'll just give like a high level overview, and I strongly suggest you guys to look into it in the future yourself, like either read a paper or watch some sort of video. But in general, it's pretty complex to like this architecture is like more complex than you think to fully understand it. But anyways, transformer uses some sort of mechanism called attention, which you probably all heard of at some point. So like the fundamental difference from attention compared to sequence model is it's like traditional neural network that it looks at all the input all at once right now. Like so it goes from like before the traditional neural network looks at everything all at once, and then they develop sequence model which looks at input one by one, but they realize it's too slow. So they come back to this idea of parallelization that you look at the entire input all at once. And however, what's the difference is that you'll form some sort of correlation between the between each word or token in this example, and each word would assign like each word would be able to look at all the other words in the input. So it's kind of like at one neuron you get all inputs from all previous neuron or previous like activations, right? So it's kind of the same idea, but here each word will assign a what we call attention weight to every single other word. And this attention weights will tell this current words how those other words will impact my meaning. So it's kind of like you here as an example, right? So for the bank example we had before, it's like the word bank itself would assign a very high attention weight to words river or money because those words has a lot of impacts on what this bank words means by itself, right? Because words has like intercorrelation, so each word would impact all other words' meaning in the context, right? Because every single word in the sentence are context dependent, somewhat, right? So they're trying to simulate that through attention. So basically, attention is like here I'm like a word myself, but my meaning is also impacted by all the other words surrounding me or in the input. So I'm trying to find which word is like important to me or can impact my meaning. Does that make sense?
Are the same always the same for the same.
Um, K, Q, and B. Let me see. They are, I think they're the same. Um, but that's like more explicit mapping. That's what they use to do this kind of attention mechanism, and this is called like self-attention. Uh, they use like KQ and B mapping to do self-attention. We're not diving into it because otherwise it'd be too complex to do. But yeah, you should look into details afterwards though. It's pretty important. Yeah. So yeah, so attention is the backbone or like the fundamental parts of transformer architecture. But transformer itself uses encoder decoder architecture. So encoder, um, as in my like it just my sounds on a page is like compressing high level of information. Like it encodes information into a lower dimension latent space. Right. So you're trying to take a huge amount of data and then you try to compress it as much as you can. So make it smaller, but still carry sort of information that you need to make whatever task you're trying to do. So that's an encoder. And in the diagram on So like the green block here is the encoder of the transform. So the green block on the left, that's the encoder, right? And then here you have like n times, so it means like you have n numbers of blocks. I think in the original paper they used like 6 or 8, I forgot. Like the same number of the same block to form an encoder. And there's also something called the decoder, which, as it sounds, it decodes low dimensional information back into high dimensional data that we kind of like human can understand, like I don't know, like words or something like that. Right? So here on the image on the right, this like larger green blocks is the decoder of the transformer. So you have like one encoder and then one decoder, and this is also stacked by n numbers of times. I think it's probably 8 in the original paper. Yeah. And they also use this sort of they use a mechanism called multi-head attention. So it's a variation of the self-attention we've seen before, but it's just a bit more complex. And in fact, it uses 3 variants of this multi-head attention too. So you have like the normal multi-head attention, you have something called masked multi-head attention, or you can call it causal attention. And there's also something called multi-head. This is supposed to be cross attention. So these are 3 different variants of the same mechanism. Uh, we're not diving deep into why they use these variants, but on a high level, multi-head attention you can think of as pretty similar to this. So yeah, it's basically the same thing, but by multiplies by different numbers of times. And masked attention is that it will mask all the future inputs, future tokens, to prevent you from seeing future information. That's like why we need a mask on a high level. And cross attention is basically it tries to unify the output from the encoder to the decoder. So they tries to combine the like basically cross attention connects the encoder and decoder together. So that's why I call it cross attention. Yeah. Hopefully that makes sense a little bit, at least on a high level. But if you want like details, that's pretty complicated. But at least the good part of the transformer models is because it allows to look at all the input all at once, then it means we're able to do parallelization again. So it's very fast, right? Also, you see transformers are filled with blocks of encoder and decoder, right? And then we call them the transformer blocks. So in reality, when you're building a new model, you want to build a very big model. What you can do is just you can stack lots of these transformers blocked together to form a very, very big model. So it's very like scalable to a large model. So yeah, and transformers are, as you probably already know, it's pretty much the backbone model for lots of like, I'll say like 90% at least of the modern architecture. So it's pretty important that you understand what transformer is if you want to learn more about machine learning. But we'll like round up our discussion for this right here. So any questions? No? Okay. So now let's talk about a little bit about phase 2. So yeah. So first, I say congrats to finishing phase 1. Yeah, you should be very proud of yourself for making through this long, basically entire semester of extra course. So yeah, we're very proud of you, and you should be proud of yourself. You should learn a lot of things about machine learning right now, like until now. So yeah, congrats. And so in phase 2, though, you'll have the chance to apply all these the knowledge you learn or even more. So yeah, so you'll learn about machine learning projects workflow, and then you'll see some of the example projects we have probably in the first week, I think. And you'll also get to know people. So you'll form a group of 3 to 4 people to do one project. So if you have like friends or whatever you are thinking of working with, you can already start forming your team even now. But we'll have like time for that in the future too. Um, yeah, and you'll learn about how to like properly scope a machine learning project. And I think one of our directors will give you a proposal workshop. So basically tells you kind of how to like scope your project and then how to convert that into a valid proposal. And we, as the director, will look at your proposal and then gives you feedback on saying, oh, maybe your project is like too simple or too hard. So basically gives you some feedback before you start working in case like it doesn't work. Like, yeah, and you'll have the chance to decide your own projects. So you can work on whatever you want, but like your group decided, right? You can work in all different kinds of domains that you're interested in, and you also gain helps from us. So if you have like any questions, we'll be here to provide support for you. And in the end, hopefully by April or late March, you'll have your potentially your first machine learning projects too. So hopefully that's exciting. Yeah, and here's the current timeline we have. This is like subject to change, but we'll just walk through it first. So for the first week, we kind of like recap and then show you some like typical ML projects and workflow. And then you can start thinking about your team, of course. And the second week, we'll do a proposal workshop, and then you'll have some time to work on your own proposal with your team. Um, and the third week is so basically kind of give you a week to work on your proposal. And by the third week, you should have your proposal submitted, and then you can submit earlier, but we'll provide you feedbacks during that. Shouldn't be during the reading week, but like we'll to try to get it back to you guys ASAP, based on the time we have. But basically, once you receive our feedback, you can start working on the project, and then for the rest of the duration, for the rest of weeks, it's basically work time. Yeah, and then we'll be here to provide support for kind of like office hours time. So last, let's talk about what you can go after, like where you can go after this phase one, because well, like machine learning has infinite directions, right? And like probably after this section, like this session, there's no one gonna tell you like us make a schedule and then like weekly learning for you to learn about one topic each week, right? So basically you're on your own going from here. And you can do like a million kind of things, right? Here's there's like a few potential common paths that you can walk down through. Like you can learn about more advanced architectures, like diving deep into CNN, RNN, or transformer, right? And those are considered even very basic architecture, and they're like a lot more advanced architecture building upon those things. So yeah, or you can do like some domain-specific application, like you can work in CV, or you can work in natural language processing, RL. There are all different kinds of domain you could work with, and then you can, uh, yeah, you can do projects on those domains depending on your interest. Or there's something very popular recently, not really recently, but it's like popular for a while called agentic workflow. So it's like you have multiple models. So for now, like basically for our scope, we're just talking about one model, right? No matter how complex it is, it's just one model. And agentic workflow refers to that you have like multiple models um, collaborating together to like work on some complex tasks. So it's like kind of instead of one person working on a task, you have like a group of people and then they all have roles, and like how you divide the work is like how you communicate, right? All those kind of things are called agentic workflow. Or you can participate in Kaggle competitions if you want. So whether you know it or not, Kaggle is a platform that allows you to participate. So they will have different kind of challenges throughout or problems for you to solve, right? So typically, if you participate in a competition, they'll post the competition, like post the problem and data set, and you'll have like I don't know, a month or a few months to work on it. And in the end, based on the leaderboard, you'll have chance to win some big money, but it's pretty hard to win in Kaggle. But that's definitely like a good project idea if you want to work on something because Kaggle basically provides you the data set and everything. So it's like a lot easier to get started with. And or you can also do your own projects based on your own interest, right? Or you can do something like paper reading to read about, which is more like research direction. But the point is, there's like infinite amount of things you can do, and these are very overwhelming. So my suggestion is that, well, in the end, machine learning is a tool, right? So that's why you see machine learning in all different kinds of domain because it is not like really a thing on itself. Rather, it's like you're using it as a tool to try to achieve some goals or sort of like solve some sort of problems. So my suggestion for you to going from here, because I cannot tell you like I cannot give you like 2 year schedule on like what to learn every single week within the 2 years, right? You are on your own. But my biggest suggestions I could give or like advice I could give is to first figure out why you want to do machine learning, right? Like what kind of like so you have to figure out your motivation behind that. Like why do you want to do it? Like kind of, what problems you want to solve with it, or um like whether you want to solve a problem or build something. Um so you have to figure out the why first, right? And then you have after you figure out what you want to do with it, you can start learning because you have like a clear goal or direction to go into. Then you kind only that you know what to learn, right? Because you know, oh, I want to build this project and I don't know about this like model architecture, whatever. So that's what I need to learn about. So figuring out your figuring out your motivation will give you like clear direction where your learning should go towards. And in the end, hopefully that will lead to a solution and goal. So yeah, that's my advice I could give you. And yeah, so that's pretty much it. I say thank you for joining us for phase one for so many weeks, and congrats, and hopefully see you all in phase two.
This is what I'm saying, that's still done.
Yeah, so,
My stuff. Also the, that will be. Oh, oops.
yeah, sorry guys. As an announcement, this week we do have notebook, but we're not walking through here. It would be like more of a take home, and it's a pretty long notebook. It includes lots of the architectures we talk about, like CN, RNN, and a lot more. So we'll post it on the web. Did we post it already?
We will post it.
Yeah, we'll post it on the like cognitive class platform and also the website. So soon, right?
Yes.
Probably by today. So yeah, you can go home and look at it. We'll post both the solution and the like exercise. So if you want, you can like look at it. But we're not going through it here.